Hi, it's Paul Bamberg. I just learned that when I made this recording back in 2014, I forgot to switch on the microphone. So let's try again with some audio. This recording is about a script that mimics perfectly the proof that the product of the determinants of two matrices is equal to the determinant of their product, and all I'm doing here is illustrating this with some randomly generated first 2x2, then 3x3 matrices. So let's start out with the 2x2 case. I'll generate a matrix A by generating 4 random numbers. That's what the function RUnif does, in the range from -2 to +2, and then by specifying the number of rows, I turn this into a nice 2x2 matrix. There it is. I do exactly the same thing to generate a second random 2x2 matrix. Then I do 2 calculations. First, I calculate the matrix product of A and B. Remember, that's what %* does in R. Having done that, I calculate the determinant of A and the determinant of B and multiply them together. And as you see, I get the same answer in both cases. Let's make up a name for the matrix product of A and B. Let's call it C. And now I want to point out to you that the way we make the first column of C, that's C blank comma 1, is by taking the matrix A and matrix multiplying it by the first column of B. Now let's try doing this in a slightly different way. What's the first column of B? Well, it's the first standard basis vector with 2 components, E1.2, times the entry in the upper left-hand corner of B, B1 comma 1, and then I have to add on to that to get the second component, B2 comma 1, that's second row, first column, and I multiply that by the standard basis vector with a 1 in the bottom position. And when I do that, I get exactly the same vector. Now let's rewrite that again. A is a matrix. It acts linearly, so I can move A through, let it act on E1.2 to get the first column of A, let it act on E2.2 to get the second column of A. There's another way to write exactly the same thing, and now that I've seen how to do this, I can just replace 1 by 2 and make the second column of C in a similar manner. So now I have a way of writing the matrix C in terms of the columns of A. I use cbind to put the 2 columns together. First, I use the expression that gave me the first column, and then, following that, I use the expression that gave me the second column. And there it is. This is just a rewrite of the matrix C. Why did we do this? Because finally we can exploit the linearity of the determinant. Remember, the determinant of a matrix is a function of the columns of the matrix, and it's a linear function. That means that when I take the determinant of this matrix C, I can expand the result above into 4 terms, one with B1, 1 and B1, 2, one with B1, 1 and B2, 2, one with B2, 1 and B1, 2, and the last one with B2, 1 and B2, 2. But, in fact, 2 of these 4 terms are going to be 0, because if I take the matrix whose columns are both equal to the first column of A or both equal to the second column of A, they will both be 0. So there is yet another rewrite of the determinant of C, and if I have the built-in determinant function, calculate the determinant of C, I get exactly the same result. Only one problem here. If you look carefully at line 24, you'll see the first term has A first column, comma A second column, while the second term has a second column followed by a first column. They're in the opposite order. That's okay. I can swap the two columns provided I change the sign of the term, and now I have a common factor of the determinant of the matrix I get by binding together the first and second columns of A. That's just the matrix A itself. And what does that get multiplied by? You'll recognize that expression as just the determinant of the 2 by 2 matrix B. Or, if you want to write this out in much more concise notation, we've shown that the determinant of C is the determinant of B times the determinant of A. Once you understand that, you'll see exactly how to do the same thing with 3 by 3 matrices, and in fact you'll probably agree with me that this proof will work for matrices of any size, that we'd have to invent an appropriate notation. So let's do the same thing in the 3 by 3 case. I make a random 3 by 3 matrix. Now I'm generating 9 random numbers from a uniform distribution, a random matrix B, and again here the determinant of the product is equal to the product of the determinants. I'll give it the name C again. In fact, I'll level it with you. What I did was copy my 2 by 2 code and edit it so that it worked for the 3 by 3 case. As in the 2 by 2 case, I note that I can make the first column of C by letting A act on the first column of B. As before, I write the first column of B in terms of the 3 entries in that column multiplied by appropriate unit vectors. For example, B1, 1 in the upper left-hand corner times E1.3. That's the 3-component vector, which is a standard basis vector because its first entry is 1, its other 2 entries are 0. As I did in the 2 by 2 case, I can rewrite this and express the first column of C as a linear combination of the columns of A, where the coefficients are the 3 entries in the first column of B. So now I have a way of writing matrix C in terms of the columns of A. There's the first column. There's the second column where I've replaced 1s by 2s. There's the third column where I've replaced 1s by 3s. And if you look at the more mathematical version of the proof that you're learning, you'll see there's actually a much more concise notation for this. In this case, I really can't honestly say that doing this in R adds very much. Okay, we expand this. The determinant is a linear function. It's a linear function of 3 vectors, each of which is the sum of 3 terms. So if we expand it, we get 27 terms. However, 21 of them are going to have a duplicate column, so they don't count. And the other 6 are all going to involve column 1, column 2, and column 3 in some order. That means they'll have the determinant of A as a factor. And this basically will complete the proof. That means the determinant of C is going to be the determinant of A multiplied by some function of the matrix B. This function of the matrix B is the same function no matter what A may equal. So if I let A be the identity matrix, C is equal to B in that case, and therefore this mysterious function must be the determinant of B, and we have proved that the determinant of the product A times B is the determinant of A times the determinant of B. Now you should go back and practice doing this yourself using summation notation.